Welcome to today's Explainer. We're diving straight into something that doesn't always get the spotlight it deserves: electronic enclosures. Think about it. Whether we're talking about a massive industrial controller, a life-saving medical device, or an EV charger on the side of the highway, we tend to obsess over the complex circuit boards inside. But those electronics, let's be real, they're basically incredibly fragile brains. And what does a fragile brain need to survive out in the real world? It needs armor. So today, we're going to unpack the meticulous multi-physics engineering that goes into designing the perfect enclosure, that vital shell that stands between our tech and total destruction. To put this into perspective, just imagine the stakes for a second. You've got a highly sensitive control board, right? And its deployment environment is a massive food processing plant. It's not just sitting pretty in some quiet, climate-controlled server room. It is going to be subjected to IP69K testing. If you know that standard, you know it means this thing will be repeatedly blasted with high-pressure, boiling steam jets. If literally a single drop of that boiling moisture sneaks inside, the system shorts out and the entire factory line goes down. So how exactly do you engineer a box to take that kind of beating? Well, here is our roadmap for building that armor today. 1. Decoding environmental standards. 2. Material selection, plastics versus metals. 3. DFM, plastic injection molding. 4. DFM, metal enclosure fabrication. And 5. Thermal management and EMI shielding. Let's jump right in. Section 1. Decoding environmental standards. You have definitely seen these alphanumeric codes on industrial gear or even just your smartphone. The IP, or Ingress Protection Rating System, is this brilliantly simple 2-digit code. The first digit measures your solid defenses, ranging from 0 up to 6. A 5 means it's mostly dust protected, but a 6 means it is completely dust tight, like even under strict vacuum testing. Then the second digit dictates your liquid defenses, scaling from 0 all the way to 9K. A 5 can handle low-pressure jets, a 7 survives temporary submergence up to a meter, and that intense 9K rating, that means it can take a direct hit from a high-pressure, high-temperature steam jet. But here's the catch. If you are designing for the North American market, IP ratings really aren't the whole story. You've got to talk NEMA ratings. The core difference here is that while IP is an international standard strictly focused on ingress, so just solids and liquids, NEMA goes a critical step further. NEMA evaluates environmental threats that IP completely ignores. We're talking corrosive agents, oil, coolants, and even testing whether external hinges and latches on the box still operate when they are literally encased in solid ice. And that perfectly highlights why official NEMA ratings are an absolute must in certain industries. Take a NEMA 4X box, for instance. It gives you all the dust and hose-directed water protection of an IP66 enclosure, but that X signifies a crucial additional layer: corrosion resistance. If you're designing for an offshore petrochemical rig or a meat processing plant using harsh caustic cleaning chemicals, that NEMA 4X spec is completely mandatory just to keep the enclosure itself from dissolving over time. Section 2. Material selection, plastics versus metals. If we decide to go the plastic route, two engineering thermoplastics pretty much dominate the conversation: ABS and polycarbonate. Now, ABS is a fantastic budget-friendly option. It takes surface textures really well and it's quite rigid. But it has limits. It'll start to deform under prolonged heat at around 97 degrees Celsius, and it breaks down under UV light. Polycarbonate, on the flip side, is your premium choice. Yes, it's going to run you about 30 to 50% more in cost, but the trade-off is incredible impact resistance, natural UV stability, and it stays heat stable all the way up to 132 degrees Celsius. Plus, because of its amorphous structure, it can be made optically clear, which is perfect if you need indicator windows or lenses. But let's be real, plastics simply can't solve everything. There are specific, hard triggers that tell an engineer, okay, it's time to abandon polymers and pivot to heavy-duty metals like aluminum or steel. You're going to make that shift when your application demands immense structural strength to survive physical impacts or severe vibration. You also pivot to metals when your internal electronics are generating heavy thermal loads that require serious heat dissipation, or if you absolutely need inherent electromagnetic interference or EMI shielding. Finally, extreme outdoor exposure, especially near salt water, often mandates the unmatched rugged durability of stainless steel. Section 3. DFM, plastic injection molding. Okay, if you're injection molding, the golden rule of DFM, designed for manufacturability, is draft angles. As hot injected plastic cools down inside a steel mold, it shrinks. It naturally contracts and grips tightly onto the mold core, generating massive surface tension. If your enclosure walls are perfectly straight, when the machine tries to eject the part, you'll get severe cosmetic scratches, or worse, you'll physically break the plastic. To stop this, you've got to design in at least 1 degree of draft angle, which is just a slight taper, for every 1 inch of cavity depth. This guarantees the cooling plastic releases smoothly and cleanly from the tooling every single time. Section 4. DFM. Metal Enclosure Fabrication.
Now, if you're designing an aluminum extrusion, you have to completely shift your mindset. Your absolute biggest enemy here is unequal metal flow. You're pushing a heated metal billet through a steel die. Thin zones and thick zones are going to flow at totally different velocities. The metal races through the thick areas and essentially starves the thin regions. To keep your profile from twisting, tearing, or warping right as it comes out of the press, you need to remember this maximum ratio. Keep your wall thickness variations to 2:1 or less across the entire cross-section.
So let's look at how we can optimize this to really drive down your tooling costs. Hollow shapes are notoriously the hardest and most expensive profiles to extrude, mostly because they require really complex porthole dies and mandrels. So if your CAD shows a multi-void hollow, take a hard look at it. Can you convert those multiple separate voids into a single larger unified cavity supported by internal webs? Or even better, if a cavity is literally only there to route a few wires, can you convert it from a hollow to a semi-hollow just by adding a small controlled slit? These sound like minor tweaks, but they drastically speed up production and significantly increase the life of the die. Over in the sheet metal enclosure world, the focus shifts entirely to bending. Every bend adds much-needed rigidity to your box, but if you push it too far, the metal fractures. The general rule of thumb for your minimum bend radius is that the internal radius should equal the material's thickness, or 1t. But you really have to respect the specific material you're using. Aluminum, depending on its temper, is way more prone to cracking than mild steel, and it often demands a larger 1.5T bend radius so it can form smoothly without totally compromising the structural integrity of that corner. Section 5. Thermal Management and EMI Shielding. Thermal management relies heavily on the material choice we made back in Step 2. If you've got really hot components, like power supplies or inverters, aluminum is absolutely your best friend because it naturally conducts heat away from the sensitive stuff. The sheer beauty of the aluminum extrusion process is that it lets you build cooling fins right into the exterior of the enclosure itself. You are maximizing your surface area for heat dissipation without needing to bolt on separate expensive heat sinks later. Of course, if passive cooling just isn't enough, you have to do the math. You need to calculate the required CFM, cubic feet per minute, of airflow to properly size an active ventilation fan so your enclosure doesn't accidentally turn into a tiny oven. And here is a massive reality check. You absolutely cannot treat EMI shielding as a late-stage Band-Aid. Electromagnetic interference can completely wreck a device's functionality. If you went with a plastic enclosure, you have to plan for secondary operations, like spraying conductive copper or nickel paints on the inside walls or utilizing specialty metal-filled plastics. Now, if you chose a metal enclosure, sure, you have natural shielding, but you aren't off the hook. You still have to engineer your seams, your gaskets, and your ventilation holes perfectly from day one. Otherwise, you might accidentally create an antenna effect that literally leaks radiation. At the end of the day, designing the perfect enclosure is this incredible, high-stakes balancing act between environmental protection, material science, and hard manufacturing constraints. So I want to leave you with a provocative thought to chew on. Take a look at your current hardware project. Are you over-specifying a crazy expensive NEMA 4X stainless steel box when a simple IP54 polycarbonate enclosure would do the trick? Or worse, are you leaving your brilliant, fragile electronics completely exposed to a hostile world? Getting that balance perfectly right, that is the true art of enclosure design. Thank you so much for joining me on this explainer, and I'll catch you in the next one.